Um, I'm Ken Burns. I'm the chair of the Science Subcommittee for the ILR here, and we are sponsoring this course, which involves conversations about climate, which Ellen is going to lead for us. Ellen, we're delighted to have with us. She spent 30 years of her life in the Miami area as an investment manager, saving money for people. And she said enough of that, and she decided to move to possibly a more natural area of the state in Gainesville, and to worry about saving the planet for all of us, which possibly is a more rewarding way to go. She had an extensive background. Suffice it to say, she had quite a few years as a reserve ranger with the U.S. Park Service in the Everglades. She's led many people safely past alligators, et cetera. And she's going to see if she can get past this group this afternoon. So welcome, Ellen. They're a pretty mild group, so you're probably okay. But this is different than many of our other talks in the ILR, because Ellen really wouldn't mind if you interrupt her at various points during her talk to raise issues about points she's just made, et cetera. And we're going to see if we can have sort of an extended conversation. She's interested in people not only learning about the environment and climate, but in getting activated to possibly do something about saving the situation to the extent that we can. So welcome to Oak Hammock here, Ellen, and good luck with this.
Ken went completely off script. That was fabulous, Ken. I'm glad we're taping it so I can get a transcript later. One thing missing, besides I have, your typical college education and a master's degree in social psychology, I also moved to Gainesville because of the University of Florida, and I enrolled in wildlife ecology and climate science courses for the last 3 years, because although I've been doing climate education for over a decade, mostly in Miami before I moved here, and then COVID, of course, I really wanted to have some depth to what I was teaching. So I'm not a PhD scientist, but I am a climate communicator, and I have certificates from a half a dozen different organizations that train people like me, lay people, to talk to other lay people. So I've been accused of having a soft voice. I have one person in the middle, and I'll assign the lady in the green and the red in the back. If you don't hear me, just let me know that I went soft again. I'm going to try really hard not to do that. As Ken said, this is a different model than your normal classes. I do want participation. I'm going to give you lots of opportunity to do so. And to our crew on Zoom, let me just look at Zoom. You're a good crew. I've got a helper, Julianne, God bless her, is monitoring your pictures. So I invite you to unmute your cameras so she can see your beautiful faces. And if you would like to contribute, she's going to look for hands. She's going to look for the little reaction thing at the bottom of your screen where you can raise a hand. So she's going to look for a little yellow or brown or white hand if you want to say something. And she's also going to look in the chat for when we invite you to participate. So you are here with us fully, folks on Zoom. Thank you for logging in and being climate heroes and heroines. So without further ado, let's go look at this program. We're calling it Whale Poop Can Save the Planet, which of course is the hook. But before we get there, we're going to share a screen. Let's see if we can get that to work.
I got it.
Okay. Well, let me open the slideshow. Let me go to Zoom. Lower the lights. Thank you.
Can you still see?
I can still see.
Okay.
I'm still disabled. I'm so sorry.
Oh,
Stand by. We love technical difficulties. Okay. Huh.
got it.
Yes. Okay. Okay. Folks in the room can have a slide. Nope. Okay. Hang on.
Remember, we want your PowerPoint open on yours, but I'll share it to the group here. There we go.
Here we go. Nope. There we don't go. You're sharing to the group, but I need to share to the folks in the audience.
No. Mine is showing on Zoom and in the audience.
Thank you.
Your notes are just for you. So you can
Thank
go to your
you.
note screen.
Got it. Okay. Perfect. Perfect. Okay. So the title of this class is Whale Poop Can Save the Planet. And of course, that's just a hook to get you curious about how is that even possible. But we're also going to be talking some science. So the way that I design each class is a little bit of it will be science so that we all have the same working vocabulary. We're going to look at the impacts of the science. When you understand what's going on, then you'll understand the impacts on us, the planet, other people, plants and animals. And finally, a little piece of each class will be devoted to solutions. What can we do individually, collectively, politically, policy-wise, to the best of our own, each person's ability? So each class will have those three sections in it. So today, the science we're going to look at are trees and wetlands, oceans, soils, ice, and what happens when carbon dioxide becomes rampant. Because carbon dioxide is, of course, natural. So I am going to invite you to take notice while we go through the class of anything that you didn't know already that surprised, pleased, or shocked you. And I'm going to kind of ask you to share that at the end of the class. So it's not a quiz exactly, but I would like to have you highlight what takeaways you're going to have here. So I want to distinguish carbon dioxide for you. It's a natural part of our air, our atmosphere, which is this little blue ribbon. So my friend wants to highlight the blue ribbon on the slide. That's working. Thank you very much, Julia. That's our atmosphere. That's been formed over about 3 billion years. And it's mostly nitrogen and oxygen and some greenhouse gases. We'll talk about greenhouse gases in another slide. A very small part of it, naturally, 0.04% is carbon dioxide. And that carbon dioxide is like Pac-Man grabbing heat. And so we're going to see a little bit of a video about what's going on. How does the carbon dioxide trap the heat? But it does trap the heat. That's regular carbon dioxide. We breathe in oxygen, we breathe out carbon dioxide. Trees breathe in carbon dioxide during the day, and they exhale a little bit of carbon dioxide during the night. But when they breathe in the carbon dioxide, it's a freaking miracle. Photosynthesis to me is a freaking miracle. Can you hear me okay? I saw the hand. Okay. Wasn't sure if you had a question. Thank you. The plant breathes in carbon dioxide and takes water and sunlight energy, and through a miracle of photosynthesis, turns it into carbohydrates, and then things eat the plants, and then other things eat those things, et cetera, et cetera, et cetera. And we're at the top of what's called a trophic food chain. We're at the top because we eat everything else that started with something that did photosynthesis. So it's a miracle, and it evolved over billions of years. So that's a good takeaway. That's natural carbon dioxide. What we've been doing since the Industrial Revolution is feeding carbon dioxide into the air with every single bit of coal, oil, or gas we burn. And we burn tons and tons and tons, something like 22 million tons of it a day going into our atmosphere. So that little blue ribbon, which is all that keeps us from freezing to death from the cold of outer space, is really essential to our life here on Earth. And we are creating this heat trapping blanket that's getting thicker and thicker and thicker. So I wanted you to understand between rampant and regular carbon dioxide. So let's take a look at, these are all very short clips. Okay, so we're going to take a look at the greenhouse effect, and Juliana's going to play that for you.
By now, you've probably heard of global warming and climate change. It's why the Earth is seeing a long-term shift in its weather patterns. But one thing you might not know is how something called the greenhouse effect leads to it. Let us explain. When the sun's rays hit the Earth, the majority of that heat bounces right back out into space. But a small portion is absorbed by chemicals in the Earth's atmosphere. These are known as greenhouse gases. Under normal circumstances, this is actually a good thing. Like a glass greenhouse that makes it possible to grow plants year-round. The heat trapped in our atmosphere by greenhouse gases helps keep the Earth warm enough to sustain life when the sun isn't shining. It only becomes a problem when we start messing with the formula. Since the dawn of the Industrial Revolution, human activity has started to change the delicate balance of chemicals in our atmosphere. By using fossil fuels like coal or petrol, we emit excess greenhouse gases, mostly in the form of carbon dioxide. More greenhouse gases mean more heat trapped in our atmosphere and, over time, a warmer planet. And that's how we get global warming. By raising the average temperature of our planet, even by a few degrees, we see some pretty dramatic effects.
And now we're going to take a look at what just 1 degree of warming is. I want to distinguish something else for you, because when you read or listen to the news about temperature, it's okay. They talk about a degree, but they're almost always talking Celsius. So you've got to mentally multiply it by 2. 1 degree Celsius is like 1.7 degrees Fahrenheit. So if they talk about global warming heading to 3 degrees Celsius, you know, well, that's not so bad. In my house, it goes from 73 to 76. I can handle it. It's not. It's like 5.4 degrees, and you can feel that. So I just want you, every time we talk about, for the sake of simplicity and matching what's in the press, we're talking about Celsius, but I'd want you to, in your head, to go double it. Okay.
Bye.
Yep. Nope. Next one.
By now, you've probably heard of global warming and climate change.
You should be able to just, yeah, there you go.
There we go. I'm
There
sorry.
it is. That's all right. We're practicing a different system than we usually use, so thanks for your patience.
For more than 10,000 years, the average global temperature didn't change by more than 1 degree Celsius. But then humans started burning fossil fuels, around here. Today, global temperatures have risen about 1 degree Celsius since pre-industrial times. This is what that looks like so far. Storms have gotten more intense. Wildfires are more common, and ancient glaciers are melting faster and faster. And that's just 1 degree of warming. Without global action, the world is on track to warm at least 3 degrees Celsius by 2100. This would be catastrophic. That's why most scientists agree that we need to limit global warming to this range, between 1.5 and 2 degrees Celsius. Carbon dioxide, which is emitted when we burn fossil fuels, accounts for most of the world's greenhouse gas emissions. It's the main culprit behind climate change.
Okay, so again, 3 degrees equals 5.4 Fahrenheit. And you saw some of the impacts, which I'll ask you in a little bit to add to your own knowledge. I want to look again at the carbon cycle. This is a cartoon.
For more than 10,000 years, the average global temperature...
I keep trying to change slides.
I know. It's tricky. Yeah, with the videos, you have to hit like the arrow twice or hit it twice. So we're looking, and we want the little cartoon for the carbon cycle.
But I interrupted you.
No, that's fine. There you go. Okay. So I want to just dive a little deeper where the carbon comes from. That's called a source. And where it gets absorbed by nature, that's called a sink. If you look at the arrows on the left side of the cartoon, they're going up in the air, and you can see that the forest burning and the tilling of the soil, the bulldozer, are letting carbon dioxide up into the air. And on the right side of the cartoon, you can see that there's carbon dioxide being sucked out of the air by trees and by the ocean. Those are called sinks. Definition of a carbon sink: a natural ecosystem that absorbs atmospheric carbon, pulling it out of the air. I'm hammering on the word sink because when I started learning this, that didn't make any sense to me. To me, the sink was in my kitchen or my bathroom or the laundry room, and water went down, and I couldn't make the connection. So it took me a little bit of getting it, that it's really pulling something out of the air. It's not exactly sinking it, but it's taking it out. And that's the word you'll read when you start looking at the literature. So besides forests, other natural sinks are mangroves, seagrasses, the phytoplankton in the ocean. Phytoplankton are the microscopic plants that live in the ocean, and they actually do absorb a lot of carbon dioxide. The great prairies of the world, the savannas around the world, and all of the mycorrhizae in the soil that support plants, all of the underground things under trees and plants, those all are carbon sinks. Okay, next slide. Okay, so this gets a little complicated, but stick with me. Look at the gray bar on the left, and can you read? That's the amount of carbon dioxide emitted before the Industrial Revolution, which started in 1750. So can you see that it's 300? Can you see the 300? Can I see a thumbs up? Yeah, okay, good, thanks. I appreciate it because I'm not a TV with a remote control, so it helps to have the interaction. That's how much was emitted before the Industrial Revolution. Now look at the black bar. That's how much we've put into the air since 1750. So that is, adds up to 500. They're measuring on that scale on the left, parts per million. So if you have a box with 1 million parts of air, they're measuring how much carbon dioxide is there. And before the Industrial Revolution, the highest we ever got was about 300 parts per million. The last time that we had something like 500 parts per million, the earth was pretty much flooded and Noah was floating his ark. It's a little dramatic, but it's been about 3 million years since we were at a total of 500 parts per million. So, but we're not at that now today. We're moving in that direction very fast. You saw that little red line in the second little video. What's keeping us from that? If you look at the little blue bar, that's what the oceans have taken out. And if you look at the little green bar, that's what the forests have taken out. So it brings us down to the red bar. Now, this is kind of an older slide. So if we can see the next slide, but only click once. Okay, don't click it again. You're going to click it twice.
Okay.
Okay, right. Okay, so this is for folks in the room and folks on the Zoom. Where do you think we are parts per million as of basically last month? Take a wag. A wag is a wild ass guess. The best you could be is wrong. 450. I hear 450. I hear 450. What do I hear? 600. I hear 600. What do we got in the chat? 420. We got 420 now. Do we have chat people? Zoom room people, you're playing too. Anybody?
Anything yet here in chat?
Nobody putting anything in chat? Come on, chat people. Wake up, wake up.
Oh, wait, someone did. 425.
425, okay. Click that slide again.
Wait, oh, sorry, I gotta get rid of my chat.
Okay, pretty close. You guys are like on it. I mean, 600 would be we're dead. We're dead. There's like too many fires, too many floods, too many droughts, too many melting ice cubes, I started to say, too many melting glaciers. But that's where we are. And what's really interesting is that we knew this was going to happen. In fact, the very first scientist who predicted the heating of the planet because of carbon dioxide was Eunice Foote, American scientist, married to another American scientist. She wrote a paper. She was the very first one to say this is going to be a problem. And because she was a female, she wasn't allowed to deliver her paper, so her husband did to the National Academy of Sciences. So lots of people have been predicting that this would happen and have been predicted the results of what would be, including scientists in Exxon back in 1988, a NASA scientist, James Hansen, also in 88. All of the presidents have been advised that this is going to happen. It's going to be a problem. And it doesn't matter who's been in administration, that number keeps going up. And it is, someone said 421, we are on track to be 421. So it is a serious, serious policy problem. Okay, next slide. I wanted to make the point here that trees are a carbon reservoir. Not only do the leaves sink the carbon into the leaves and turn it into carbohydrate, but they take it and put it into the ground below ground. So this is a picture, pretend, of the Amazon, and when you slash and burn, not only do you stop sequestering carbon, but you also release carbon that's in the tree, and you release all the carbon that's in the soil. And because most of the Amazon is being slashed and burned to raise food for cattle or pasture for cattle, this is a big problem. So one of the things that you can think about is where your meat is sourced. I'm not saying don't eat hamburgers. I'm saying look at where the beef is coming from and what went into getting it to your plate or to McDonald's, God forbid. Okay, next slide. Thank you. Not yet. This is by David Johnston. He was the director of an Amazon research base. He's British. He went to the Amazon as a scientist, fell in love with it, moved there, bought some land to save the land, and is dedicating his life to forest conservation. My colleague, Tiffany Duong, provided this little 3-minute video for this class. So I'd be interested when we're done what your takeaway is. So when you watch it, see what happens to you as you watch it. I say it's very short. Thank you. Okay, I invite the Zoom roomers to put in the chat any impact this video had on you, and I'd invite 2 or 3 of you to share. Thank you. What a great question. What is palm oil? Remind me to repeat the questions. The question is, what is palm oil used for? If I said everything, that covers it. Start reading your labels. Palm oil is one of the monoculture, meaning that's the only tree they plant. If they clear cut a forest and decide to replant it, very often a company will come in and plant palm oil trees. But that's all the trees they plant, so you don't have the biodiversity. And they use the palm oil for everything from lipstick to shampoo to it's in your food. So it's literally in everything. If any of you ever watched Grace and Frankie, remember, oh gosh, who's the funny lady? Jane Fonda and Lily Tomlin. There's a whole thing about they invent a vaginal lubricant and she sells it to her daughter-in-law who uses palm oil instead of more expensive regular oil. And it's a whole thing about palm oil, which is where I got introduced to, well, what is palm oil? So I thank you for that question. Okay, impacts, question.
Want to look at your chat up there on the screen?
Oh, sure.
It says we can do better, depressing and we must change. What about landscape foliage?
Okay, landscape foliage does have a positive effect. What would be better is not to cut old growth forests down in the first place and not to cut rainforests down in the first place. And in Brazil, we now have a shot at a president Lula, who might let things stand. Okay, how does replanting a forest affect it? Replanting a forest is a very, very good idea. However, it takes a very long time for a forest to grow. So it's way more effective not to chop it down in the first place. And we're going to look at that in class 5 under solutions. We'll take a good look. Yes, ma'am.
Has anybody seen the video of the orangutan attacking the heavy equipment that's tearing its home out?
The comment is there's a video of an orangutan attacking the heavy equipment that's tearing his home up. Wow, that has to be emotional. Yeah. Yes, ma'am. Last one. There you go. Yes. Okay. So this person is commenting that when she looked at the maps and saw the burning over just 20 years, that Europe burnt, Sweden burnt almost to a crisp. It's really amazing, right? It's worldwide. It's not just the Amazon. What surprised me was Canada, because Canada's got so much freaking land. It's like, how can you have all that much burnt? And I lived there last summer. It's like, oh, okay. All right. Somebody's dying. Yes. One more. Yes, there's a trillion tree project, and there's a billion tree project, and there's a 1 million tree project. Those are super if you plant the right tree in the right place and you take care of it. So there has been, I actually do have a video that doesn't fit in this class, it's just not enough time, from the guy that invented the billion tree project. He got it going, and he's heartbroken because the trees weren't done in the right, thoughtful way. Everybody thought, just plant a tree and I'm good. So when you do plant a tree, think about where it's going, think about what it needs, and think about, does it belong in the place you've planted it? And in terms of equity, which is a whole piece of climate change, in terms of equity for Indigenous people, if you are going into an area where Indigenous people used to live and you're going to replant it for them, make sure that you're replanting the trees that were burnt down in the first place and not planting trees that don't fit. Thank you for that question. Okay, next slide.
One more comment.
One more comment. No, I appreciate that. Yes.
Says, is it most of this pressure on the forest a result of overpopulation? Wouldn't global warming in essence solve this problem?
The answer is there is overpopulation and it is pressure on food sources. But if you look at where that land is going, I said it before, I'll say it again, you may not be aware of it. 70% of our agriculture, our use of water, our use of land is used for soybean and corn to feed cows. It's cows. It's not that cows are bad. It's what we're feeding them is bad. And that's not what they're supposed to eat in the first place. And there's a whole regenerative agricultural movement about moving cows onto pastures, planting the original grasses that were there or wild grasses, and moving them around because the cows eat, then they poop, they recycles the nutrients, it plants the seeds again. So the answer to that question is no. Okay, one more. Yeah, right now, right. The question is, what about red meat? Right now, red meat is a huge user of our resources, not the overpopulation of people. In fact, if you look at the carbon footprints of third world countries versus the United States, it's horrifying. Our footprint is this big and their carbon footprint is this big. They don't use the resources, and they're hungry. The issue is most of that land is going to feeding first world people who want beef. Yeah. Well, we've got to make a change. We need a cultural and a societal change. And we have to figure out ways to eat beef that don't do that. Okay, thanks. Next slide. So we've been looking at land. So let's take a look at the oceans. Okay. So remember what I said about the basics of climate change? That it's making more carbon dioxide in the atmosphere that makes a heat trapping blanket. It traps more radiation, causes warming of the planet. So we're stuck with not only more heat, but also more carbon in our atmosphere. So where does it go? Well, we looked at the little slide with the blue bar and the green bar. And so a majority of it actually is going into the ocean. But the oceans are getting a little too hot. Even the very deep ocean, the 4,000, 5,000 foot parts of the ocean is getting hotter, which has a lot of implications for currents and nutrient exchanges, a lot of problems there. So how much is it? Next slide. You can see that land the earth takes in some of that heat. But you can also see that most of it, actually it's 93% of the extra heat it generated is going into our oceans. So our next animation needs some attention. So I'm going to point your eyes to the, not yet, well, yeah, maybe you could open it, but don't start it. Okay.
This link?
No, next slide.
Next slide, sorry.
Yeah. There you go. Don't start it
Okay.
yet. Okay. You see up in the top where it says 1940, that's a time clock. It moves very quickly but through the decades. So you kind of want to watch that. Can you point out Florida? Yep, very good. Okay, so that's where we live. I just like you to anchor to the parts that are blue are the water and the parts that are white or gray, depending on what screen you're seeing, are land. Okay, so just watch that. And watch what's happening. Where's the heat going? Go for it. Okay, and this is a graph. If you look at the bottom, they're going down to 2,000 meters. That's like times 3 is 6,000 feet. So they're a mile down. Very deep water, should be very, very cold down there. And you can see that it actually got warmer and warmer and warmer. And this clock stops at 2016 and everything you see is just getting worse. Okay, next slide. So that's what's happening to the heat. The heat in the ocean causes a lot of coral bleaching and it also causes animals to migrate north to colder water. So Maine lobster will soon be Canadian lobster anytime now. The other thing that happens is something called ocean acidification. We need a chemist to come back here and explain it. Suffice it to say that the ocean acidification is not good for things with shells, and this cute little cartoon will show us that.
Invisible force invades world, slowly dissolving residents. Sounds like science fiction. Actually, it's science nonfiction, otherwise known as reality, and it's happening right now. It is ocean acidification. The ocean absorbs about 1/3 of the carbon dioxide that spews forth from our cars, factories, power plants, and airplanes. That's over 22 million tons of CO2 a day. But the ocean doesn't just absorb all that CO2. There's a chemical reaction going on here. Through processes involving hydrogen ions and other sciencey nonfiction words, the ocean is becoming more acidic. And that in turn is eroding the shells of vital marine species, including clams, oysters, urchins, and pteropods. Oh, sure. I know what you're thinking. Who cares about a bunch of pteropods? But these animals are part of the foundation of an enormous food web. And when little things change on a big scale, big changes are sure to follow. The chemical change in our seawater is also having an effect on corals. In fact, scientists say that ocean acidification could wipe out most coral reefs by the middle of this century. It's affecting larger animals too. For example, certain fish have a harder time detecting predators, and that's just for starters. The good news is that with less carbon pollution, the ocean should regain its chemical balance. If not, the truth will be a lot scarier than fiction.
Okay, how are you guys doing? Throwing a whole ton of crap into your ears, right? Yeah, I get it. I get it. It's hard to live with this knowledge. And I understand if some people just go, no, don't want to know, like why I won't go watch bloody movies. It's like, no, I don't need to see that. Reality's bad enough like that. Hang in with me. It is dire, and there's lots of things happening, and we're about to move into where I will share some of the things we have available to us right now with present technology, present finances. This is a completely fixable situation. It will just take political will. We have technology, and we have finance, and we have willingness at grassroots level and at some of our policy level to reverse what's going on. We're not completely out of time. We're on a very short timeline for sure. We should have started 30 years ago, but we can do it. Is anybody dying to say something before I move on? Yes, ma'am.
We have no choice.
We do have a choice. We can do what they did in that movie, Don't Look Up, and just let everything implode. But we here are too old to see the total implosion. It's our children, our grandchildren, our great-grandchildren that are going to inhabit a world that is uninhabitable. But we do have to do something. Of course we do. Yeah. Okay, last comment. Yeah.
What is the end game of all this?
What is the end game? The end game to my program, is that your question? Yes, the end game to my program is wherever you are on the scale from very alarmed to completely denial is to move you one little notch up. And if you're already completely alarmed, like I am, to move you into supporting me in these programs. That's my end game. Does that answer your question?
Not quite. What is the end game to everything that's going on the planet that is having a negative effect on almost everything?
Okay, so you're asking what is the end? Okay, the question is, what's the end game? Business as usual. We keep burning fossil fuel. We don't do anything about population control. We don't do anything about converting everything to electricity, which is provided by renewable energies. The end game is by end of this century, we will probably have hit 3 degrees centigrade, 5.4 degrees Fahrenheit, and everything you've seen now that is smoke choking you for your family in California, or hiding the skies because you can't see the sun, or the hurricanes that Florida has just experienced, every single thing that's already unbearable will simply get worse. Plus, you will have inbound and outbound migration from countries like Asia and Africa, where the droughts are causing severe famines and the floods are repositioning millions and millions of people, plus deaths. So the end game is not pretty. My professor, Dr. Mulkey, and some of you may have been here the evening he came, and he would be very happy to come speak again. So I was really delighted that he had a good experience here. He predicts that if we hit 500 parts per million, civilization as we know it ends, and only about 500,000 people will be able to be supported by what's left of Earth. That's your end game. But I don't have a crystal ball. Last comment, yes. If the oceans die, about 2 billion people who depend on the oceans for food have nowhere to go. And yeah, right. The end game is life as we know it. civilization as we know it has crumpled. It's really serious. I mean, got to take it seriously. But my end game is to move everybody here up a tiny little notch. And you'll see at the end, my last slide is what those notches look like. So thanks for hanging in. We're getting to the hopeful part. Yeah. Photoplankton, phytoplankton. Phytoplankton, yes, oh, hang on. The question is, what about phytoplankton? Wait for the whale poop slide. It's coming. It's coming. Okay. Next slide. Thank you. Thank you. Terrific conversation. Okay. So I know this is one more devastating piece of information. The Arctic is melting. We looked at the little program that was done in 2020 that said we're at 1 degree centigrade. We're actually probably more like 1.25 degrees centigrade. Parts of the United States have heated up 1.7 degrees centigrade. Remember, double that, so that's about 3.4 degrees Fahrenheit. The Arctic, which we will get to in another program, is actually heating 4 times faster than the rest of the planet. Yes, and what's happening there is frozen peatlands and permafrost are melting. So besides melting and houses falling into the ocean, which is bad enough, when it melts, it's releasing old carbon dioxide, old methane, and worst of all, hello, Ken, bacteria and viruses that have been frozen for millennia. We don't know who they are or what they're going to do to us. So that's kind of like, the gorilla lurking behind the closet door. It's not out all the way yet, but it's on its way. So permafrost is scary. And when we till soils, and I mentioned that earlier, when we till soils the normal way we till soils, it releases carbon dioxide. There are no-till farming methods that are easy to adopt and can be adopted. So one of the things, if you're interested in farm lobbying, is making sure that we support regenerative agriculture and that kind of thing. Okay, next slide, cartoon. Okay, here's something you can share with folks. It's simple. The emissions are coming into the bathtub. There's a certain high level of carbon dioxide already in the atmosphere, shown as water in the bathtub, and there's a very skinny drain of water coming out of the bathtub. That represents the skinny drain of what normal, natural, regular carbon dioxide would be doing. It'd be getting sucked up by plants, phytoplankton. So it's a summary of the situation. This is the dynamics of rising carbon dioxide in our atmosphere. It enters like water coming into a tub, and it leaves like water getting out of a tub. And what we have to do, it's got to be obvious, if your tub was overflowing, you would turn the tap off before you went to get the mop and bucket. So step one is turn off the emissions. To quote Dr. Mulkey, what does that mean? It means kill fossil fuels now. It means do everything in your power to talk our power company right here in Gainesville to go into renewables. And a bunch of us have been working just on that, and they don't get it yet. And if they get it, they're not acting on it. Their comment is, it's too expensive, we're too small, we're not ready, blah, blah, blah. But cities our size have successfully done that. So just bear that in mind. That's something we could do locally if you happen to be oriented towards the activist type of activity. Lots of activities to take. The other thing is increase those net removals. One of those things would be, we're getting to whale poop, would be plant more trees, do not deforest. We're going to do a whole class on what that looks like. So that's just kind of the graphic of what's going on. So let's take a look at what nature has already given us here in Florida. Next slide, please. Okay. There's a name for these. Nature has provided mangroves, marsh grass, and seagrass in the ocean. And the name that we've given this is blue carbon sinks. A green carbon sink is the trees, a blue carbon sink are the things in the water, kind of easy to remember. So here's hope. I mean, these things work. And mangroves are the best possible plant. Here's why. I'm from South Florida, as Ken said. Actually, I was there for 44 years. It was just 30 years as an investment manager. And that's right. You did a great job. That was really a terrific introduction. and I really am going to transcript it. Mangroves have really thick leaves. They sequester a lot of carbon. They don't all fall off. They're not deciduous. They drop one at a time. And because the leaves are so thick and waxy, when they fall to the bottom, they don't disintegrate really fast. They help build up soil. And little things, crustaceans, bacteria, algae grow in the leaves, and then all the little other things start eating that stuff, and then other things eat the stuff that's eating the stuff on the leaves. So mangroves are phenomenal. Plus, that root system really holds, hi, how are you? Really holds dirt. And so the mangrove not only helps sequester carbon or sink the carbon, the mangrove holds the land together when there's a hurricane or a storm surge. So houses protected by a large fringe of mangrove trees will not, like the poor houses on the East Coast in Nicole, fall into the freaking Atlantic Ocean during a hurricane. So but I'm not talking about that part just yet, just that they are really, really good carbon sinks. Next slide, please. Okay. Some of you are more scientifically oriented, so I thought I'd throw this slide in for you. This Coke's for you. Also, I know some of you may have to leave early, so when they stand up, don't worry about it. It wasn't that I did a bad job. It's okay, they just had another commitment. Okay, so if you just to real quickly look at the picture, you can tell by looking at the graph on the left of the cartoon part, that's dollars. You can see that mangroves have an extraordinary value to wherever they're planted. They clean the air, they protect the shoreline, they feed a whole ecosystem of things that end up on your dinner plate eventually. So that's kind of a good way to take a look at it. Okay, I'm not going to, in the interest of time, I'm not going to go through what A, B, and C are. Basically, they just show which one does better overall, which one does best at density, and which one sequesters the fastest. What you see, maybe, let's see if you see the same thing I see. If you take a look at that graph, you can throw it in the chat, Zoom roomers, and maybe those of you for whom the print is not too small can see overall which habitat is the best overall for us.
Am I a slide behind? Am I a slide behind?
No.
Oh, okay.
Oh, wait, yes, you are. Sorry.
Okay, sorry.
You want the one with all the bars.
Okay.
I apologize. Thank you. Okay, let's start over again. This is straight out of my class with Dr. Mulkey, so you can read the statistics. But as you look at the graphs, the blue is ocean, the brown is soil, the little green is forests above ground. Can you see which? And at the bottom, it says open ocean, forest, peatlands, and coastal wetlands. You can see that. Okay, which one wins? Anybody? Coastal wetlands does a good job. And overall? Yeah, look at peatlands. Peatlands are being cleared, burnt and cleared, and peatlands sequester a ton of carbon because they're like very, very ancient. And when you burn them, we're letting all that carbon out, and what gets planted on top of them doesn't sequester as much. So, but these are the natural carbon solutions we have, so we should leave them alone. Okay, next slide. Here we are. Here's what you all came for. Get out the popcorn. Okay. This is my friend Rachel Crane. She works on National Geographic Alaska boats. She's a marine ecologist. She also does a lot of teaching of children, so she's a little bit, I think, she has a style, but she's very smart. She's PhD. She loves whales, and this will be 12 minutes. So before we start, I want just to introduce a concept that she will introduce again. It's called a trophic cascade. So I talked before about trophs are levels of where you are on the food chain. And if you knock one thing out, a cascade like dominoes has a big impact. So she's going to introduce a trophic cascade, and you're going to go, what's that got to do with whales? So just keep your curiosity open, and she will tell you what it has to do with whales. Whales are different. Take it away,
My
Joanne.
name is Rachel Crane, and I am a marine ecologist. That means that I love learning about living organisms in and around the ocean and how they interact with their environment. You guys have all been learning about blue carbon, ecosystems, and biodiversity loss. So I would like to take all of these things and put them together in a story to illustrate just how connected everything is to each other. To do that, we are going to talk about one of the most mind-blowing and inspiring animals on our planet, the whale. All right, whales. The great whales are the largest living things on the planet, and they survive by eating some of the smallest critters in the ocean. The great whales it's just an umbrella term for all the enormous filter-feeding baleen whales, like the humpback whale, the blue whale, the gray whale. These whales basically use their baleen to feed, kind of like how a man uses his mustache to catch all the goodies. The great whales play a vital role in driving and maintaining the health of numerous marine ecosystems. This slide just highlights a few of them. The great whales are involved in an ecological process called a trophic cascade. Simply put, it's science speak for the enemy of my enemy is my friend. The most famous example in marine ecosystems is the food chain made up of the sea otter, the sea urchin, and kelp. Otters eat urchins, and urchins eat kelp. When sea otters are removed from the top of the food chain, the sea urchins have no major predators and run rampant, eating all the kelp and destroying the ecosystem. The enemy of the kelp is the sea urchin. The enemy of the sea urchin is the sea otter, which means that the kelp and the sea otter are friends. So when we put the sea otters back into this type of ecosystem, they eat the sea urchins, thus increasing the kelp and maintaining the health of the kelp forest marine ecosystem. This illustrates how a trophic cascade is an ecological process which starts at the top of the food chain with the presence or absence of sea otters and tumbles all the way down to the bottom, determining the presence or absence of kelp, and in this case, of the entire kelp forest ecosystem. So let's apply this to whales. We know that whales eat fish and krill. So one line of thinking is that killing whales is good for human beings because it will boost the amount of fish and krill available for us to eat. Less whales, more fish and krill for us. And while today your gut reaction might be to not like that logic, it does kind of make sense. Unfortunately, it's also the logic that prevailed. And for better or worse, we're actually able to learn how our ocean is functioning with only about 25 to 30% of its historic whale population. Because in the 1900s, nearly 3 million whales were killed in what is one of the largest mass killings of any animal in terms of total biomass. Whales are really heavy in human history. And the researchers think that 3 million is a lowball estimate. It's too big a concept to fully digest. This extreme loss of a top predator has had a surprising and confusing effect on marine ecosystems. And it took us a while to understand, because what happened was that as the great whales declined, so did the numbers of fish and krill. It seems counterintuitive. Surely the numbers of krill and fish would rise as their major predators disappeared, the same way the urchin population exploded with the loss of sea otters. But even after commercial whaling was banned in 1986, there is still less krill in the oceans than there was before commercial whaling started in the 1900s. In fact, scientists have determined that krill abundance has declined by as much as 50% since the start of commercial whaling, and actually continues to drop. So what gives? It turns out the scientists need to look a step lower in the food chain to unlock the mystery. Normally, if an apex predator, whale, is removed from the ecosystem, their prey population, krill, explodes, and the prey's food source, in this case phytoplankton, which are just teeny tiny photosynthetic algae, these guys should decrease due to overgrazing, like the sea otters, urchins, and kelp ecosystem. But instead, with the mass removal of whales, there's been a decrease in krill. So then shouldn't there be an increase in the phytoplankton since they aren't being eaten by krill? That's good thinking, right? But it's not happening either. Everything in this food chain is decreasing. But why? And let's think logically for a moment. Doesn't this suggest that the only way to fix this entirely downward trend is to undo the one massive change we made? Do we need to increase the whales to increase everything? As it turns out, scientists discovered that the answer to that question was the key. Yes, this food chain is in a league of its own. This trophic cascade is like no other. Whales not only eat krill and fish, they also keep them alive. In fact, whales help to sustain the entire living system of our ocean planet. How do they do it? Well, whales are moving and grooving in the oceans around the world. Many whales have to dive down deep to feed, but they always return to the surface to breathe. The surface is also known as the photic or euphotic zone because this is where there's enough light in the ocean to facilitate photosynthesis. And while they're at the surface, whales typically release what biologists call fecal plumes, or poop, vast outpourings of poo, punamis, if you will. And turns out whale punamis are rich in iron and nitrogen, two nutrients which are often very scarce in the surface waters of the oceans. You may recognize these are ingredients for fertilizer, and you would be correct. Both of these nutrients are vitally necessary for healthy phytoplankton populations in this photic zone where photosynthesis is possible. It turns out whales fertilize the photic zone. Whales are farmers. But fertilizing the surface waters isn't the only thing that the whales do. By plunging up and down in the water column, whales bring nutrients from the depths up to the surface, and they keep kicking the phytoplankton back up into the photic zone, giving it more time to photosynthesize and reproduce before it sinks into the abyss. Migrating species take this vertical up and down movement on the road, mixing the entire ocean as they go about their lives. Even today, with the whale populations having been greatly reduced, the movements of all marine animals up and down through the columns of the oceans is astonishingly roughly the same as the amount of mixing caused by all the world's winds, waves, and tides. But there's more, because phytoplankton is vastly important to the health of the entire ocean, the entire planet. Phytoplankton is not only the base of all marine food webs, they have global significance. They affect every living thing on the planet because they photosynthesize on a grand scale and are responsible for half, 50%, every other breath you are taking of all the oxygen in our atmosphere. Crazy, right? It gets better. Through that same photosynthesis, phytoplankton absorbs CO2 and thus carbon from our atmosphere. They capture an estimated 37 billion tons, or 40% of all carbon dioxide produced in a year. That's 4 times the amount of carbon that the Amazon sequesters in a year, and the equivalent of 8 billion cars worth of yearly emissions. That's almost a car per human on the planet. When the phytoplankton eventually dies and sinks to the ocean floor as marine snow, it takes this carbon out of circulation, down to a place where it remains locked in for thousands of years. The more whales there are, the more plankton there is. The more plankton there is, the more carbon is drawn out of the air. This trophic cascade is more of a true cycle. There are no enemies here. Everyone is friends. Whales, krill, and phytoplankton act together as ecosystem engineers, helping to maintain global marine and terrestrial ecosystem health. protecting and conserving whale populations so that their numbers can start to recover to their pre-whaling status could be seen as a form of biogeoengineering, which is a type of climate engineering that seeks to take advantage of or modify, grow more of, the existing plants or other living things that naturally adjust the Earth's climate. More whales equals more phytoplankton. So if we can increase whale populations to the point that they can facilitate increasing phytoplankton productivity by 1% globally, it would be equivalent to the sudden appearance of 2 billion mature trees. That's exciting. And the excitement for this is catching on. In an effort to help governments understand the importance of letting whales live, the International Monetary Fund, IMF, has recently estimated the value of a single great whale to be worth over $2 million if it is left alive to live out its life in the ocean. This knowledge can help emphasize the importance of whales in the language that our governments speak, money, and spur improved and altogether new management practices are put in place to better protect whales and our oceans. Saving the whales could undo some of the damage we have done both to our planet's marine ecosystems and to our global atmosphere. Whales are important. Whales are ecological engineers. Whales help maintain the global health of marine ecosystems. Whales change the climate. All we have to do to help is let them live. My name is...
Yeah. Okay, thumbs up, you loved it? Thumbs down, didn't like it? Okay, we got thumbs up. I love that show. Okay, I know we're at time. Can you hold it while I just wrap up, and then folks who need to leave can leave? Okay, and then we'll take some more questions from the Zoom room. We're going to jump right to my last slide, which I promised you. So what can you do? I'm going to challenge you, kind of, if you will, a homework, not really, but a homework assignment. As you go through this week, focus your attention on whatever news sources you read, conversations you have with friends and family. See if you can come back with an insight, a nugget of information, anything that helped focus your personal attention on climate change, big or small. I'd like to see what we can create together. And this is a research paper by Elise Amel, and this is her graphic on what to do. You can see the top little circle that says person, that's us. And so when someone said, what's the end game, sir? The end game is to take yourself from personal and move yourself up a level or two as a result of this series. I do these series wherever I can, because the best thing you can do to combat climate change right now is keep talking about it. Let me give you a scary statistic. Back in 2020, Bureau of Climate Communications did a study of Americans, red and blue and purple, and something like 72% of Americans acknowledge climate change is real. Deniers are now in the ever very, very sharp minority. 67% of Americans agreed it's caused by people, and this data is 2 years old before we've had all the fires, droughts, hurricanes, polar vortexes that we've had, okay? 37% of Americans will talk about it. And so climate scientist Catherine Eo, who happens to be an evangelical minister as well as a climate scientist at Texas Tech, points out that the best thing you can do personally to do something about the changing climate is start talking about it. Take that 37% up and see if we can't move it around. And that can be a little scary. So I challenge you to think about where you fit in that this week with your friends, your colleagues, your garden club, your book club, your grandkids, whoever. And notice that you can learn something. You can donate money and time. You can walk instead of drive. You can reduce and reuse things that are in your life. You can take those personal steps. And here's where I will tie the tie the knot so that folks who need to leave can leave. And we had a question. Yes.
You think you don't have any power personally. You have never slept in a room with a mosquito. And I approach this from a point of view of being a Christian. Somebody said, would you be a mosquito for God? I said, yeah.
Yep. Yep.
That's what I'm called to do. So we're all supposed to buzz around and let people know this is real and we're supposed to do something about it. You can start buying products that are made by green companies. That's a whole other thing. But
Yeah, I've got to introduce you, Sarah. Would you Sarah, stand up. Sarah Nussel is a speaker for Climate Reality Project, which is a program we've both been trained by Al Gore. And she is remarkable. She is reduce, reuse, recycle. She will come collect your broken eggshells. She is, absolutely indefatigable. Thanks, Sarah. We're glad you're here. Any other closing comments from the group here or the group in the Zoom room? I want to thank you for coming. Next week, we're looking at hurricanes. The program next week is called What's With All These Storms? The week after that, I will be on vacation, so we're skipping the 24th of January. We'll follow that with your favorite subject, sea level rise. Yeah, right. And we'll take it from there. Class 5 will be actions you can take, and Class 6 is going to be how do you talk to people about it, which gets to a question that came from the back. So you've been marvelous. Thank you for collaborating. I thank you. You are rock stars. This is not an easy topic. I'm not opening your head and pouring in data. I'm opening your head and pouring in feelings, I hope. Okay, thanks for coming.